2, 1. So volume flow rate. When you get into fluid dynamics, this is probably one of the first items that you're gonna study. I'll do my best. I'll put the reference in the description notes in case you want to read up a little bit more. OpenStax is a very nice physics book, and it talks about dynamics in terms of fluids, and it's free, so I'll link it there for you. Now, my goal in this video is to explain volume flow rate to you, and hopefully you'll get some intuition. The formula for volume flow rate in dynamics isn't very difficult. So as you can see here, I put that the volume flow rate that you have, and I designate it in this way. Now, this doesn't mean that you're going to see this in all the textbooks. I like using the capital V just for volume, and then I just put FR, which is the flow rate. Now, some textbooks might use something different. Now, what it means is simply the total amount of volume that you have, okay, that might pass through a particular tube of some kind. Now, it doesn't have to be necessarily a cylindrical tube. However, so you may kind of wonder, in nature, you'll find that pretty much anytime you do have a fluid, which is kind of, even if it's in the trees, okay, if it's somewhere else, these are cylindrical, right? So which means if you take the cross section, you're going to have a circle, okay, or very close to a circle as possible. And there's various reasons for that. And when you study flow rates, don't think that they're all kind of tubular in a cylinder-like tube. They can be in other tubes, okay? But in this video, I'll talk about the cylindrical ones, but it doesn't have to necessarily be that way. Now, whatever volume passes through a tube in a certain amount of time, so this is the amount of volume that you have, okay, through a change in time. So some passage of time is defined as the volume flow rate. Now, what is very interesting is that this particular formula, which is actually the formula for volume flow rate, can be broken down, and I'll explain this in just a moment, as the cross section, okay, of the whatever tubular form that you have, multiplied by the actual change in distance, okay, divided by the total time. And I hope that I can explain this momentarily. Now, the SI unit that we typically are talking about, the volume, as you know, is in meters cubed. That's the SI unit, which means that the time, okay, is in seconds. So this would be the SI unit standard. Now, there is a little bit of a problem with dealing with meters cubed, because meter cubed is actually a really big unit. It's 1 meter by 1 meter by 1 meter. And that's a lot of volume if you're talking about liquids. So we, for convenience, and now this is maybe the first time that you've kind of run into this, definitely not the first time that you probably have run into liters in terms of a unit, but we do use liters very often, okay? So I designate it with capital L, so that's a very important unit for fluids, okay, for liquids that we're dealing with. And I would want you to know this, if this is the first time that you're learning about this, then you should know that actually 1 meter cubed can be divided, okay, into 1,000 pieces. And that, thousandth of a piece is actually equal to a liter. So that means 1,000 liters. So if you take 1,000 pieces together, okay, that equates it back to a meter cubed. And this is much more convenient unit for us to use, and you'll see that very often. And that's why sometimes you'll see even milliliters, microliters, liters, okay, etc. So you can, put prefixes. It is a metric unit, liters, that is. So you can put prefixes in front of it and designate it that way. And it's a little bit more convenient, okay, for us to use. Now, if you use meters cubed, or even if you use centimeters cubed, okay, or if you use liters, doesn't matter, but you should know this unit. Okay, so that's kind of the introduction with regards to that. Now, let's talk about this flow rate and the meaning behind it. So if we take some kind of a tube, and let's assume that it's uniform in nature. So, if you take this cross section, so if I take this, I'm going to kind of duplicate this maybe, okay, for myself. Okay, if you slice this at any point, we're going to assume that it's basically cylindrical. Now, if you would do that, Okay, so within here, so let's imagine that I have that. Now, no matter where I cut this, I'm going to assume that the cross section there is the same. Now, the one thing that you should know, if you take this particular cross section right here, this is, okay, what I am referring to as A, or as the area. So this is the cross section that you would have, that you would cut through. Okay, so just keep that in mind because it's going to relate back to that actual formula. So it's not very hard for us to envision. So let's imagine that we have water, and so we'll have water, and water actually flows through this. And we wanted to be able to figure out, okay, so how much water. It can be any fluid, by the way, fluid in terms of gases or liquids, doesn't matter. Okay, but water is very easy for us to understand. So if we have water which is flowing, we can indeed ask the question, okay, how much water, okay, in terms of volume has flown per unit of time, which is T. And that really is your volume flow rate, right? So this is exactly what it is. Now, how does this actually relate back? Because the water is flowing at a particular speed, right? So it is moving. So the particles in the water are moving. Now, we should remember that, hold on a second, we know what speed is, right? So speed is kind of the change in this displacement, or the change in distance that we have divided by time. So, if I would take one singular particle, right? So let's say if I would take just one singular particle in here, and I would start it over here, and then it would end over here. So its initial position, okay, in terms of positions, in terms of placements, would be here. So this is my initial distance, okay, or initial position. This is my final position, right? And if I do that, so you may recall that so the change, so the total change, or the distance which has been covered by this particle, would have been nothing else but the final minus the initial, okay, or simply you can just simply write it as d, which is the distance that this particle has covered. Now, because the liquids, there's a lot of particles that are flowing through here, right? This is just one little particle that we have. Well, you can take this particular particle, and then you can say that, okay, well, there's a tons of particles, okay, that are flowing in here. So, there's a particle, so you have all of these little particles that are flowing by. And what my goal is, okay, well, how about all of these particles, if I counted all of them together, right? And then they would cover a certain distance. So if they would kind of be moving along all the way through, so if they were starting from this point, and then ended off at this point, and I would take all of these particular particles, so that would have been like the cross section. Now, if you take that cross section, so I've kind of mapped it out over here, and then you allow it to move, notice that it creates, okay, this cylindrical tube. So it creates all of those particles over a particular time. So if this travels over a certain amount of time, then we know that, hold on a second, that's just kind of speed of these particles, right? So, well, speed that we had, this was just little v, okay, it was equal to the actual distance that would be covered divided by the total time that would pass. Right? So that isn't anything new for us. That would be the speed of this. And of course, if you have water which is kind of flowing through here, so it's kind of moving along from one end to another, then all of these particles are moving at a certain speed. And what I would want you to think about is, all right, so well, if I take all of those particles, right? So if they're moving along here, they're moving along this tube, right? So let's say they move from that distance, from di to df. So how much would they actually cover? Well, so if I wanted to know all of the particles, then I would have to actually know all the particles on that cross-sectional area, right? So all of these guys, okay, that would be passing through. So all of these, and now, they're passing along and they're moving through. And they've moved, okay, over a time period of some, change in t, or just t itself. Okay, so this now tells me that all these particles are moving at this particular speed. Well, but that is just the cross-sectional area, right? So this is just the cross-sectional area that I have, and this cross-sectional area has now moved, okay, a certain particular distance, okay, if I take all of these into place. So what I would have is, all right, so if I take all of those particles that I have in there, so that cross-sectional area, okay? And now I multiply it, so by the actual speed in here, so multiply it by the speed, delta D over delta T. Well, now all of a sudden, so if you notice here that, okay, well, if I take all of them, multiply that by this, I'm going to just get the cross-sectional area multiplied by the distance D. I'm going to drop the delta in here, so I'll just leave it as D itself. And this, okay, is divided by how much time has passed by. But hold on a second. The cross-sectional area multiplied by the distance covered, that now creates a volume, right? So this is the actual volume, okay, of this fluid that is passing through here. So this is nothing else but volume, right, that we would have. And that, that it shouldn't shock us because, if you were thinking back, let's say if I had a cylinder and I'm going to do it vertically, right? So if I go like this, so what you would say is, well, the volume, okay, of this entire cylinder would be nothing else but simply the base, okay, that we have. So that would have been this base multiplied by its height, and that would have been the volume, okay, of that cylinder, which is the area multiplied by h. Now, in here, this is just horizontal, but it's exactly the same thing. So we have, okay, so how much volume passes by over a certain amount of time. And that is what your volume flow rate actually becomes. So this, okay, is the actual, okay, formula that we would have. And if I go back in here, so this is exactly what we had over here. So if you notice, this is the area times, how much distance has been covered divided by t. And very often, you might see this written out as simply as the area. And because all of this right here that we have in here, this is just your velocity. So this is velocity that we would have. That is actually your volume flow rate. So if you know the cross-sectional area and you know how quickly the fluid is moving, so you know its speed, if you multiply those two, you're going to know how much, okay, volume passes, every single unit of time. And that's exactly what flow rate is all about. So let's take a look at this, right? So if we wanted to be able to do something with this, okay, and, maybe actually provide some kind of context. So if I say, for instance, if I take this cylinder right here and I'm going to just copy this throughout. And let's say I have water, right? So I'm going to take this and copy it. And someone tells me, so, if I have something like this and we're able to measure, we know that the volume flow rate is equal to the volume divided by the time that passes by, or simply the cross-sectional area, okay, divided by distance times time, which is just simply your speed. So this is what it would be. So if someone tells us, for instance, okay, if I know exactly what the volume flow rate might be, so let's say, I don't know, maybe it's 10, okay, and this would be, let's say, liters, okay, that passes by, and this would have been passing me by, every single minute. And now someone comes along and says, okay, well, then over, let's say 15 minutes, okay, that would pass by. Then, how much volume has actually flown in here? Well, that means that, okay, so I know the volume flow rate, I know the amount of time, so I can certainly solve for V in here. So if I would substitute all of this in here, so this would have been, in this case, this particular equation, and then volume would have been just simply equal to 10 multiplied by 15, which would have been just 150. Now, in this case, it would have been liters, okay, that would have been passing by. So we can use these things if we know, okay, what is going on. Now, of course, if someone tells us, okay, so for instance, another example, let's call this example A, and here's example B. If someone instead says, okay, well, I know that the fluid, okay, is moving at a speed, and maybe this is moving at a speed of 2.5 meters per second, right? So again, that's how fast the actual liquid, okay, is moving through there. And then someone comes along and says, well, the tube itself, has a cross-sectional area. Now this is going to be a cylindrical tube, so I'm going to say that the radius that we have in there, let's make it, let's say 1.2 centimeters. Okay, that would have been the radius. So if we have this piece of information, we can actually find out what the volume flow rate is in here. Now, how would we do that? Well, the volume flow rate is nothing else in this case. Okay, so that would have been the cross-sectional area times your V. Now, my cross-sectional area, if we know the radius and it's cylindrical, so this is where you have to kind of remember what the area of a circle is, and that's just simply pi r squared. And then times your speed, right? So this would have been V, so you can substitute all of this in here. Now, if you want this in metric standard units, because you have to be careful in here, so notice this is meters, right? This is in centimeters, so we can certainly turn this back in. So it would have been 0 point, okay, and then 0.12, so that's changing the prefix in there, squared, multiplied by, and this is your speed, which is 2.5 meters per second. So now we will know exactly what the volume is. So if I take my calculator out in here, so this would have been pi multiplied by 0.012, and I'm going to square that up in there, and then multiplied by whatever the speed, okay, of that fluid is. So there we have it. This would have been 0.00113, etc. I'll keep it to two significant figures. Now, this would have been in meters cubed, and this would have been per second. Now, if you change that back to liters, so don't forget that we have 1 meter cubed is equal to 1,000 liters. So if you want to change that back in there, so you can certainly get rid of the meters cubed. So this would have been actually shifting this over 3 places. So this would have been approximately 1.1, as I said, to two significant figures for this. And this would have been just liters per second. So every second there is about 1.1 liter, okay, which is flowing by. And this is exactly, okay, what we see in here if we're going to be calculating these style of questions, and it gives you some kind of a sense, what do you have to do? The formula itself is not very difficult, right, to be able to deal with it. And you have to be careful and see, okay, which formula am I going to use? Is it this one? Okay, is it this one? Or is maybe volume given? So this is something that you have to understand. Now, for the next topic, okay, that I want to be able to kind of finish this video off with, that I want to be able to present to you, is very often when you do have fluids, and this is for, by the way, incompressible fluids, which most of the time would be liquids. We have to be careful. Gases, we can compress, and very often we can compress quite a lot. But liquids, okay, and liquids of course are fluids, we can't really compress, okay, or we can compress very little. And in those instances, there's something very interesting that happens. If you have, okay, and so notice that you have 2 tubes and then you have a narrowing of a tube. It's almost like you can think about, if you have your hose, okay, and your hose is, relatively thicker, but then your nozzle is very, very, it's very tiny, right, that we have, and yet we notice that, oh my gosh, if I spray out through this nozzle, it really, the speed that comes out, okay, is super quick, right? So this might be coming out at a very fast pace. Okay, however, what is interesting to note is that because of the fact, let's say that this, okay, is, much wider than obviously this, okay, so this is much less than that, then it turns out that if you know what the volume flow rate is, the volume flow rate will be continuous throughout. So just because one, okay, is much thicker than the other, if you do the narrowing, it turns out that the volume flow rate, so let's call this, piece number 1, and let's call this piece number 2. So it turns out that the volume flow rate in piece number 1 is going to be equal to the volume flow rate in piece number 2. And that is just because of continuity. Now we're assuming there's no blockages or anything like that. It's just kind of flowing throughout, okay, that we have. Now, Because of this continuity, okay, in terms of the volume flow rate, that's going to tell us something. Now, clearly, the cross-sectional area over here is much bigger than the cross-sectional area over here. So the only thing that can possibly change, so if you're going to be looking at this, okay, from here, this is going to be the cross-sectional area of unit 1 multiplied by whatever speed that is moving at. And it is equal to the cross-sectional area, okay, of this tube, okay, in 2 multiplied at whatever speed this is moving at. But if these two volume flow rates are supposed to be equal by continuity, so they're equivalent to each other, well, clearly, this is not equal. So this cross-section, okay, and this cross-section, those are not equal. But overall, if the whole thing is equal, that means that these speeds have to change and they have to adjust. And of course, what happens is, okay, if these liquids, okay, are flowing through here, because they have much more volume to be able to flow through, okay, the speed over here is going to be much slower. And when you narrow this down, the speed over here is going to start to increase because it has less, that cross-sectional area to flow through. So it has to speed up if it still wants to maintain the total volume flow rate as it had originally here. So that is very neat, okay, for us to be able to see. And that is why if you hook up a hose, you'll notice that if you create a nozzle and that nozzle has, a very small little thin opening, then it's going to, spread out, okay, very fast. It's going to come out very quickly. And yet over here, it's going slowly. And it's just abiding to this continuity flow. And that's very neat, okay, what happens. And again, this only happens for incompressible, so liquids that can't be compressed, okay, at least not that much. And so this will hold more or less true. Let's see this through an actual example and how we can apply this throughout. All right, so let's look at this example. All right, so now our goal in here is to find out, how fast is this fluid flowing out. So again, we can imagine it's water. Okay, so that's going through. And what we notice is that, so here's the cross-sectional area, okay, which is over here, okay, this is the radius, and then this is the radius of this. Now, the only thing we know is what is the speed that it's moving at, okay, on that fatter portion. Okay, so in this case, what we know is that the volume flow rate, so that the volume flow rate, okay, of piece number 1, let's call this piece number 1, is going to be equal to the volume flow rate of piece number 2. And let's say this is piece number 2 over here. Now, if this is the case, then from over here, what do we know? Well, we know that this is equal to the cross-sectional area multiplied by the speed, okay, that it is moving at. I'm going to put 1 and 1 over here. And that's going to be equal to the cross-sectional area of number 2 and the speed that it's moving over here. Now, we're after this, right? So this is what we want to be able to find. So if this is what we want to be able to find, we can certainly divide both sides by the area, okay, of the second piece. So that's going to be this times, okay, divided by, and this is going to be piece number 2. And now we can solve for this directly. So let's substitute all of the pieces of information. We'll assume that it is indeed circular, okay? That cross-sectional area. So it's going to be pi. Now my R1, which is 1.1 centimeters squared. And this is going to be multiplied by, this is 2.5 meters per second. All right, so that's what I have there. And this is going to be divided by pi, and this is 0.32 centimeters squared, and that's supposed to be V2. Now, you might wonder, and you might say, well, hold on a second, you're not consistent with your units because you have centimeters in here. Now, you can change it to meters. You don't have to, because actually you have centimeters squared on top and you have centimeters squared at the bottom. So the units okay, of that radius is going to cancel. It doesn't matter if you keep it in meters, okay, or if you keep it in centimeters or any others, as long as those two are consistent. So this won't actually cause us a headache. Now, from here, you do notice that, okay, the pi will cancel. So that's gone, okay, within here. Now I can just substitute everything back in. So what does that equal to? So I have 1.1, and this is supposedly squared, multiplied by 2.5, and then divided by, it's going to be 0.32, and again, this is squared. So that's what I have in here, and notice what happens. So this is 29.54. This is going to be meters per second. And, so for this one, I just want to take a look. Okay, everything was 2 sig fig. So, I'm going to round this off. Okay, so this would be approximately, 30 meters per second. Okay, V2. If you wanted to do significant figures, of course, you can put it in scientific notation. In this case, like this. And notice that, how much faster it's flowing out. It's flowing out at 30 meters per second. And over here, so as you saw over here, this was only at 2.5 meters per second. So that's quite an enormous change, okay, that we have. And the reason for that is because that cross-sectional area, is that much smaller. And because we have the squared component, okay, it's going to boost this speed up quite a bit. So this is something which is very useful to be able to understand when you are covering, okay, flow rates, okay, and in particular volume flow rates within, tubes in general. All right, so that is it for this video here. So I hope that it gives you some kind of context, okay, and introduces you to the concept of volume flow rate. Thanks for watching. See you in a future video. Happy studying. Bye, everybody.